Okay, you can continue.
Okay, sir. What's a home energy management system? It's a computer-based control system which is installed in the buildings to monitor and control the building's electrical and mechanical equipments, where many of the researchers are now focusing on the key issues like real-time intelligence and resources scheduling, demand response, and adaptive controllers like temperature or thermal comforts, adaptive controlling, and optimization techniques and peak valley uh, issues, peak valley balance issues, and forecasting of the demand and generation, and artificial intelligence and machine learning applications to the home management system. And National Smart Grid Mission, which is initiated by the Government of India in 2015, and Indian Smart Grid Forum, those two are working in these areas. And from this, I partly motivated, and I have slided to work in these areas, AMI and DR and DG, and smart metering and policy and business models. And four of my works are mapped against to these areas. And mainly smart grid is motivated with the upsurge in the energy demands and growing interest in the environmental issues and escalation in the fuel charges and conservation of energy. And especially demand response and energy management approaches are playing a dynamic role in obtaining the smart grid objectives. With the progress in the smart grid, computational powers and bidirectional communications and handiness of the supervisor data and mutual understanding between the utility and the consumers, and win-win situation between the utility and the consumer. And the major problems we are getting is because of the peak value issues, peak value load profiles, which is increasing the burden on the main grid, is caused by the integration of the stochastic renewable energy sources and PEVs in the grid, and because of the uncertainties in the power generation and load profiles. Best example is the northern grid collapse in India in 2012, where the northern part of India, because of the monsoon failure, overpower was drawn in that area from the neighboring eastern and western grids, where the rains, because of the floods, very less power drawn in that region. Because of the imbalance of 9% of power between the generation and demand, whatever the power drawn in the northern grid, 27% of the power was lost in the transmission itself. So because of these grid imbalances, voltage and frequency issues we will get, whereas voltages can be controlled locally and frequencies we cannot. So that's why to deal these problems locally, energy management approach and intelligent controllers are required, and optimization algorithms and incentive demand response programs are also required. And my objective here is to develop a dynamic demand response program based on the price elasticity, which is integrated with the loss aversion characteristics. This is the price elasticity, means the variation of demand with respect to the change in price. That is a price elasticity, whereas loss aversion is nothing but, with an example, I can say in the real time pricing, if you want to shift the load from peak hours to the off peak hours, in the peak hours the price will be more. So shifting from high price hours to the low price hours, it leading the consumer to move into the benefits. At the same time, in the peak time rebate demand response programs, means while peak consumption, we are offering more rebates, more incentives. So if we are shifting the load from peak hours to the off peak hours, there the consumer is leading into the losses. So the action is same, shifting the load from the peak hours to the off peak hours, but the perceptions are different. One, in first case it's leading into the gains, in the second case it's leading into the losses, but those losses and gains will not be linear, and in practical losses will be always steeper. But in many of the demand response programs, this loss aversion factor is not included, whereas the system won't be become as a practical solution. And this demand response program with the price elasticity loss aversion is tested for the different loss aversion values and rebates and the elasticity constants. And I would like to see how the price and demand curve would be changed, and we can suggest the best ways in the priorities of peak demand and load demand and overall cost with the given conditions and seasons. In the second objective, a new water filling energy based distributed algorithm uh, with PV as a second storage, without disobeying the constraints of the main system and the individual appliances is proposed, and the investigations are made, and the consequential effects on the overall cost, comforts, grid energy deviation, and the SOC of the battery and lifetime of the battery and stress on the battery are also discussed here. And in the third objective, a small prototype is prepared to make the system energy efficient home energy management system. And the complete literature work I have published in one journal, and the title is Application of Demand Response and Co-Simulation Approach, Renewable Integrated Home Energy Management System, which includes with the all the available already installed methods of measuring and metering units and the communication units, and demand response programs which are already used for the HEMS, and different optimization algorithms and different monitoring and controlling techniques which are already adopted for the home energy management system. And the issues like means if we want to implement a perfect system for the HEMS, electrical systems will be simulated in the power system simulator, whereas the communication like uh, data communication from one place to another, if you want to realize it, some communication network is also needed. But if you want to implement together, some issues will be faced, and those issues are also discussed, and some solutions are also discussed here. These are different ways of connecting smart meters with the house, dedicated line, and DLMS protocol, and IEEE ZigBee protocol, and power line connections, and internet protocols. The advantages and disadvantages are also discussed, and this is some base model where here this is the generation side. The total data of generation will be obtained from here. Consumption is obtained. Consumption data is obtained from here. It will be transferred to the home server, whereas these data again transferred to the remote energy monitoring service, and some analysis like data analysis and some controlling actions can also be done from the remote energy monitoring server also with the help of the internet protocols. And different functionalities and controllers like SCADA, FPGA, and islanding connections, islanding controlling, those are those are also discussed in the literature. And where the demand response programs are classified mainly based on the controlling mechanism and offered motivation and decision variable, where the controlling mechanism is again classified as a centralized scheme and distributed scheme, whereas the centralized scheme, the controlling and the pricing signals will be transferred from the substation to the houses here, whereas in the distributed scheme, there will be a provision to communicate among the homes, means among here there won't be any communication from home to home about their consumption and patterns, but there will be a provision among communication for the, there is a provision among the homes for communication here in the distributed energy, in the distributed scheme. And these are the incentive based DR programs. These are classified as again time based and incentive based. These are listed out here, and their suitability for the residential, commercial, and industrial applications is also listed out here. And the different optimization algorithms which are already used for the DR programs are listed out here. And one issue I would like to tell, what are the real challenges we will face while integrating the power systems with the communication systems. Actually, this is a power system works on the continuous time signals, whereas communication systems works on the discrete time signals. Whenever fault occurs in the power systems, these fault will be communicated to the communication system at the next synchronizing point only. And if it wants to rectify the issue with the, by giving a controlling signal until the next synchronization point, it cannot give. So these type of errors will be occurs in the system, and these can be avoided by using the additional solvers. And different power system simulators which are used for the home energy management system and distributed generation are listed out here: SAMDIST and eMegaSim, OpenDSS, GridLabD, and their suitability for the steady state and transients is also given here, and their suitability for generation, transmission, and distribution and residential, commercial, and industrial applications are also listed out here. And their license, whether it is open source or commercial, is also mentioned here, and their compatibility with other softwares like MATLAB or Python is also listed out here, and their applications are also discussed here. These are the smart grid simulators, means power system simulators along with the communication system simulators are used in many of the literatures for the different applications like WAMP, wide area monitoring, protection and control, and DSM, DR, and HEMS. And their suitability for the distribution system is also given here. This complete literature of my work is published in the IIT Generation, Transmission and Distribution, which is an SEA expanded and with an impact factor of 2.862. And after completion of my literature review, even I too felt that it was completely vast and wide area, and my DC members are also suggested me to narrow down my research. Then I started my work completely on the demand response and the energy management programs. In the very first work, I started with the demand response program. This is my first work, framework for the smart grid to implement a price elasticity based peak time rebate demand response program. These are the literatures I have gone through. This is a system, actually the complete data of PV generated and P consumed by the homes is obtained from the Pecan Street Smart Grid Project data port, and the model is developed, and the P grid is obtained from the obtained data of P of PV and P used, and it is tested for the different pricing signals like flat rate, real-time pricing, and day ahead pricing, which is obtained the real-time data from the Commonwealth Education Company website, and it is tested for these different pricing signals, and the total cost, total demand, and peak demand are obtained, and these are compared with the for the different seasons and scenarios. And then now peak time rebate DR program is prepared, and this is also tested for the different scenarios like loss aversion and rebates and seasons is also tested here. This is the simulation model. Actually, three-phase substation with the 13.8 kV is connected to the three-phase load and through a cable, and our residential transformer is tapped from here, which is a three-winding transformer here, which is a 50 kVA rating and 13.8 kV input and 120 volts output, where here 120, here 120, but phase opposition we will get. And between L1 and L2 legs, we will get the 240 volts with the 0 degrees. And whereas whereas it is connected with the two neighborhoods where N1 and N2, each neighborhood will consist of the 5 ohms, and their data ID from the Pecan Street is already mentioned here. The data IDs are also mentioned here for the neighbor 1, neighborhood 2 1. This is the phase opposition waveforms. And the power profiles P of PV generated and the P consumed by the homes has been taken already from the Pecan Street data port, and P grid is obtained from these two waveforms. This data has been considered for the month of February, May, and August, November, and I have taken a single day from each month. Why? Because I have taken a single day for each season also. Total 4 seasons I have taken, 4 seasons, one day I have taken. And the power distribution among the legs. Here, these legs, how the power is distributed between the 3 legs. These are the equations, and how to calculate the energy supply charges. In the peak time rebate, energy supply charges is the total kilowatt hour drawn from the grid into flat rate minus whatever the reward we are applying, whatever the reward we are giving for each kilowatt hour reduction. So by this way we can find the energy supply charges for all the pricing schemes. And this is the data of the season information, summer, fall, winter, and spring. From each season I am taking the 1 day data, and this is the price for single day from each season. DAP means day ahead pricing and real time pricing signals have been taken, and this real time pricing with the help of the flat rate price is not provided. So because of that, real time pricing we have taken, and by taking an average of that, we have taken these as a flat rate value. And now this is the proposed method. What is the price elasticity? It is the percentage change in demand with respect to the percentage change in price. So if it is linear, means the demand variation is linear to the demand change in price, then it is called the unit elastic. And if it is greater than 1, it is called the elastic demand. If it is less than 1, it is an inelastic demand. And self elasticity and gross elasticity. Self elasticity means if for particular item the change in price for the particular item will change the demand of that particular respective item is called self elasticity. The change in price of one particular item is changing the demand of the another item, that is called the cross elasticity. And single period model and multi period model, we are giving the modeling equations. Single period means some loads are very sensitive to single period only, but some loads, shiftable loads, we can shift from this hour to the next hour also. That are called the multi-period sensitive hours. And this is the price incentives provided P, and this is the benefit. This is the revenue obtained by the consumer, and these are the spot values, and these are the incentives. And this lambda is the loss aversion factor. Loss aversion factor is included here. And this is the complete demand equation after incorporating the price responsive and incentive based responsive and loss aversion responsive system. And this is for the multi-period model. And the total consumption data of the 4 days has been categorized again into the low consumption, off peak, and peak hours. And the cross elasticity values have been taken from the reference, and with the trial and error method have changed these values. And for my analysis, whereas lambda is equal to 1 is nothing but is used as a loss aversion value in PTR1 program, means loss aversion is not included. Loss aversion is considered in the PTR2 program, whereas lambda is equal to 0.5, means for a gain of x, the loss will be 2 times of the gain. Our assumption is like that. So that's why we're taking lambda is equal to 0.5 here. And in the PTR program, it is same as the PTR2 program, but we are doubling the cross elasticity values here. And in the PTR4 program, it is same as the PTR1 program, but the reward we are doubling now. So we are going to see how the system is affecting with a PTR DR program for a change in lambda values and cross elasticity values and the reward changes. So this is the result for all the pricing signals. This is for the month of February only I have taken. Here we can see this is with the values of the flat rate value, total cost, total demand, and peak demand. RTP is not showing much significant role here. It's only 5%, 1%, 1% change only. When it comes to the day ahead pricing, it's reducing the 30% of its total cost, means utility is losing its 30% of profit without any good performance in the total demand and peak demand. So it's not at all advisable. And in the PTR1 program, the total cost of the utility has been reduced to 15%, and the peak reduction is also has been taken place here with a 26% of reduction here in the PTR2, whereas lambda is considered, that is actual practical lambda is equal to 0.5 has been considered. The total cost is reduced here, and here peak demand is also reduced here to half. Why? Because that lambda value it is reduced now. And in the PTR3, where it is same as the PTR2, but elasticity constants are double now. Now with this, there is no change has been observed here in the peak demand compared to the PTR2. But here there is a considerable change has been observed in case of total demand. It's the total serving capability of the utility has risen to 9% here with a only loss of 1% of total profit. So this PTR3 has giving the moderate values compared to the PTR1 and 2, and whereas PTR4 the reward is double now. Means we are giving more incentives for the consumer. Then it's obviously it will loses its profit. It's losing 64% of its profit, whereas the peak demand is reduced to 50%. But even though it's not an advisable solution, by because it's completely moving into the losses. And this is for the February month demand, how it has changed after implementing the PTR3 program. Whereas according to our categorization table, 29 to 33 are the peak hours, and 89 to 96 are the peak hours here. Now, during these hours, 29 to 33 and 88 to 96, this red one is after implementing the PTR3. Peak demand is reduced, whereas in the remaining, we can see the red line is in the top position, means all the peak hours load has been transferred to the half peak hours. This is for the month of February. Already we discussed in the table. This is for the flat rate. This is for the PTR3. So with a very 1% of reduction in the total cost, it's giving the good performance in case of the total demand, 9% improvement and 13% reduction in the peak demand. Whereas in the month of May, with the day ahead pricing, 30%, almost 29% of the increase in the percentage increase in the total cost. So it's a good solution, but there is again it's not compromising in total demand and peak demand also. So with the same values, it's giving 30%. It's a advisable solution in the month of May. And when we are strict to only total cost, peak reduction. So PTR1 is giving the good performance with the 26% reduction, but at the same time, it's losing the 36% of its profits. So in the month of May also, PTR3 is performing better with a 9% of reduction in the total cost and a peak demand reduction of 13%. So this is between the seasons, how it's affecting the curve in the seasons between February, May, and August, November. So we can see here the total demand, the total demand served is about 400 kilowatt hour in the month of February, and in the month of May, it's almost 5 to 600. But here the price charged here is very less, even though the load is the total demand is more here, because of in the month of May, as it is a windy month, it charges very less. In the month of February, it charges 0.0564 dollars per kilowatt hour, whereas in the month of May, $0.03 per kilowatt hour it's charging. And even November is also a windy month, so it's charging very less, $0.03 per kilowatt hour. One more thing here, in the month of August and November, the total demand is same, almost same. But here again, we can see the total cost charged in the month of November is almost half of the August here. And when we compare February to November here it is 400, here it is up to again 1000, almost 120% of the price in the total demand. But the charges, if we see total cost charged by the utility, it's 20 to 30. Again, here also some 30, around 30. And this is the peak demand comparison between the seasons here. Peak demand here 26% is fixed for the PTR1 here, for the PTR1, and for the PTR2 it's reduced by exactly half because of that lambda inclusion. And even though after including the after price elasticity values are changed, there is no change in the peak demand. Peak demand is not affecting with the price elasticity changes. And here with the value of lambda, how it is changing the peak demand. So for the lambda is equal to 1, it's 26%. For lambda is equal to 0.5, it's 13% here. In all of the cases, the trend is same here. And now in the scenario 3, with the doubling of the reward, then already we discussed, it's losing the 64% of its profit for a reduction of 49. So it's not at all an advisable solution. And two more criteria also we have analyzed: equal loss scenario and peak reduction scenario. In the equal loss scenario means compared to the flat rate in the real time pricing, it's losing 6% of its utility profit. So for the same 6% of utility profit in the PTR programs, how much peak reduction we can do, that we have done here. So it's PTR1 is losing 11, PTR is doing 11% reduction in the peak demand, whereas PTR3 is doing also 11% reduction in the demand. But compared to PTR1, PTR3 is better. Why? Because its total demand serving capability also is raised by the 8.58%. And in the peak reduction scenario, means compared to the flat rate, in the real time pricing, 8% of reduction was there. So for the same reduction of the peak, how the cost and total demand is varying. Here it's 11% of reduction in the PTR1, so it's a huge loss only. So it's RTP is better one. But here total demand is also reduced by 4% here. So this is for the equal loss scenario. Already we discussed. PTR3 is giving the better performance for the same equal losses by increasing the total demand by 8% and reducing the peak demand by 11% here. And the lambda change in lambda value, how it is affecting. The change in lambda is also means lambda equal to 0.5 and lambda is equal to 1. These two, there is no much change has been seen here in the case of total demand, but peak demand is reduced. Already we discussed some 26%, 13%. So those are tabulated here. Those values are tabulated here. And if the elasticity values are doubled, already we discussed PTR3. So 7% rise in the total demand serving capability. And here 8% in the month of the August. The peak demand, there is no change with the changes in the price elasticity constants here. So this is a peak time rebate demand response programs. And this work is communicated with the elsewhere sustainable energy grids and networks, which is an SEA expanded and with an impact factor 2.532. And after completion of this, I have moved on to the implementation of demand response energy distributive algorithm based HEMS here. These are the literatures I have gone through. A water filling energy distributive algorithm based home energy management system in coordination with the PV. So these are the modeling equations of the appliances what we are taking here. These are the decision variables and the battery SOC equation for the battery and their power limitations, power constraints. Thermal storage. Thermal storage means it's used for the hot water applications of a storage tank. The temperature in the thermal storage is obtained from this equation, and these are the thermal storage constraint values, temperature constraints here. Heat pump is used for the space heating applications, whereas the room temperature is obtained from this equation, and the constraints of the room temperature are given with the equation 29. This is the CHP and HP combined unit, whereas here we are giving a natural gas as an input to the CHP. It's producing both electrical and heat also. This electrical energy produced by CHP is utilized to run the heat pump here, and it produces some heat, useful heat for the space. It will be used for the space heating applications like room heating applications. And the heat generated by the CHP is passed on with the heat recovery system, and some heat will be wasted, and remaining of the heat generated with the CHP in it, that is utilized with the thermal storage tank, and it will be used for the thermal storage tank hot water applications. This is the non-interruptible loads, washing machine and dishwasher and cloth dryer we are taking, and these are the status, and these are the constraints where it has to start and how much time it takes for completion of the task, that constraint. And this is the PV mobility equations where the SOC equation is obtained from this equation, and this is the laxity equation. Laxity is the that is the readiness of the PEV to get involved in the system based on the existing SOC and the required SOC. And this is the optimal starting times of the appliances. Here, for these optimal starting times will be obtained. For the non-interruptible appliances, it's obtained with the linear integer programming. And here also for the PEV, the optimal starting time is also obtained with the linear integer programming with the help of this. And the SOC constraints will be changed after getting the optimal integer starting time. And here, this is the power balance equations. This is the grid power taken from the grid. It's always based on the remaining all power parameters, and the power need from the power have been taken from the PEV is calculated from this. Whether it is PEVs are charging or discharging will be based on this, and this is the equations for available energy during the charging. What is the energy that can be charged and what is the energy that can be discharged are obtained from these equations 43 and 44. And now our intention is to minimize the delta P here. What is delta P? That is the grid deviation from the specified value. Why? Because we need to maintain the grid within the specified limits. So this has been taken as a variance here, and with the help of the Lagrange's values, this is the main minimization problem with the inclusion of its constraint. The total energy regulated which has been taken from the PEVs should be less than or equal to the total available energy with the PEVs. And after some mathematical rearrangements, we will get this equation, whereas mu and E of PEV regulating. This is used to minimize the E grid, has been taken from the grid. And in the water filling energy distributive algorithm, E grid specified is given as the main equation, and the constraints, what are the available energy and the discharging energy available, that is also given, and some tolerance will also be given. So the output we will get as mu, and after getting mu we will get the EPEV regulating also. So this is the flowchart of my work. The total data of pricing and PV generated and the critical loads, hot water consumption and the degradable cost and the natural gas purchase cost and the temperature settings of heat pump and as well as the thermal storage have been taken, and the temperature limits are also set by the user. comfortness temperatures for the room temperature and thermal storage are also set by the users, and those optimal timings will be obtained with the help of the linear integer programming here. After getting these optimal timings, we'll calculate the energy available in each duration and the energy that can be discharged also with the help of this. During charging, we will find the space available to charge, space available to discharge, and it will be linked with the our optimization problem, minimization of cost and maximization of comfort. These are the two objectives, but those two can be converted as a single objective problem, and it is solved by the genetic algorithm here. These are the total system input data. What is the energy consumption of the overall system, and energy storages, battery storage and its specifications, PV, how we are considering, and thermal storage, heat pump, PEV, those specification details. And these are the preferable timings for the non-interruptible appliances. So this is the hot water consumption profile of a day, forecasted PV power of a day. This is the data we are taking, room temperature of a day, critical load profile, and pricing signal, temperature of the hot water in thermal storage tank. This is the pricing signal. TOU2 we are TOU2 means only 2 times it is changing, that we are considering for our analysis. This is the cost function, which is involved with the purchase of power from the grid or giving back to the grid. So purchase cost and the battery degradation cost and PEV degradable cost and the purchase cost that is required for the natural gas in case of CHP is also involved with the cost function. Whereas in the comfort function, the thermal comforts for the heat pump and the thermal storage and the time comforts for the non-interruptible appliances and PEV is obtained. So those appliances will be involved with the comfort function here. And this is comfort level indicator for the PEV. This is optimization model. Cost function and comfort function are optimized, and with the weighing method, we are minimizing the total. This is the F total, and we are minimizing this F total with the help of the GA here. So this is without using plug-in electric vehicle and without employing the water filling. Just the same system is solved with the GA. Then we are getting the net cost and degradable cost, revenue, and the cost comfort level indicator here. And after using PEV, the net cost is net cost is increased, and the degradable cost is also increased slightly. Battery degradable cost is also increased slightly. Revenue is also increased, and the cost for purchase is reduced here. The comfort, this is the comfort level indicator value, so it is reduced. Reduced means comfort increases. It's inversely proportional, but it's not showing that much difference compared to the without including the PEV. But after including the PEV and implying water filling algorithm together, it's giving the good performance by showing 2.91 here, reducing the total cost. Battery degradable cost is also reduced, and the revenue from the sales is increased here. So significant reduction in purchase cost and higher revenue is also achieved in case 3 here. And the total, when it comes to the statistics, 12.95% reduction in the cost and 7.27% improvement in the total comfort is achieved in case 3 compared to the case 1 and 2 here. Because of the, and battery degradable cost is also reduced here as the batteries, because the consumption patterns has been changed of the appliances. Here minimizing delta P, this is grid flattening with the help of the P grid support that is obtained from the water filling algorithm. This delta P or delta E is getting reduced here, and in case of without implementing water filling, without implementing PEV, this is first one, there is no color, and with the PEV, this is cyan color, and the black one is after implementing the PEV and water filling. In the first 1 and 2 cases, it's crossing 3 here, and it's 3 and 4, -3 and 4. It's maintaining between the -3 and 4. But our intention is to minimize the delta P here. So we are fixing our constraints to the -2 and 3. So it's always maintaining the limits. It's maintaining between the 3 and 2. And at the same time, it's minimizing the total cost and improving the comfort also here. And because the employing PEV, SOC of the total static battery is also raised here. And the battery, this is the battery power waveform, and the number of charging and discharging cycles are also reduced with the by employing the water filling algorithm here. So this work is communicated and published in the Elsewhere Sustainable Energy Grids and Networks, which is an SEI expanded with an impact factor of 2.5. And after this, I carried out small prototype work with the smart meter integrated with the IoT. Actually, I have done these prototype works in the initial days of my research. And this is here we are measuring the parameters and sensing and measuring the parameters and monitoring the parameters. And those are displayed in the PC with the help of the Arduino, which is interfaced with the IoT clouds with Ethernet shield. And it is the total data will be transferred to the web pages with the help of the HTML and CSS. This is the black diagram. Sensors will sense the data and it will be measured and given to the analog to digital converter of the microcontroller, where the data will be processed and the total electrical parameters will be obtained here. So this is the circuit. Whereas this 220 by 10 volts transformer here, here we are using an adder circuit. This sinusoidal waveform is converted into the unipolar waveform, and it is stepped down to obtain the voltage within the limits of the Arduino, that is 5 volts here. And this is the frequency measuring circuit, whereas zero crossing detector was used here to convert the sinusoidal waveform into the square waveform, and to remove the negative portion, and diode was used, and it is given to the Arduino to find the time here and time and frequency here, and the current measuring unit here ASM010 current sensor we are current transformer we are using. Actually the current it is of rating 10 amperes of rating. It can carry up to 10 amperes. For the 10 amperes it will give the 40 millivolts of voltage at the burden resistor, so that is the proportionality. But this 40 millivolts is not sufficient to be detected by the Arduino, so it will be amplified with the help of the amplifier here, and we are getting some 2.4 volts, and again it is given to the adder and potential divider circuit to maintain the voltage limits between the 5 volts here. So this is the hardware circuit, voltage measuring circuit this is, and current measuring circuit. This is the current transformer. The wire will be from the current transformer inside, and this is the frequency measurement circuit. This is a voltage transformer initial output, and it is after signal conditioning, like after adder and after adder and potential divider circuit, we are getting unipolar waveform here. Negative portion is removed here, and this is the output of the current transformer. 19 millivolts we are getting, so it's not at all will be measured by the Arduino, so it's amplified here some 2.4, and again it is a signal condition with the adder and potential divider circuit to get the positive waveform here. And this is the input voltage waveform which is given to the zero crossing detector. So it's converted into the square waveform, and the negative portion will be removed. So the data has been seen in the serial monitor, and its web page is created. The data will be shown in the web page here. These are the equations that are used to find the parameters here. And this is the next ZigBee based wireless system for the remote supervision and control of the electrical parameters. So this is a circuit here. ACS712 current sensor is used, and this is a voltage measuring circuit, and here current will be measured with the help of these Arduino. Voltage will be measured with these Arduino, and these are the relays used to control these voltage and current circuits also. This is relay 1 and relay 2, and here the data obtained in the ZigBee 1 and 2 will be these two will act as the router, and this will be act as a coordinator, and these data will be transferred to the ThinkSpeak cloud with the help of the Node MCU, which provides an internet facility for the system. And at the same time, for the data will be seen in the Android apps, and we can control the appliances also with the help of these relays. Means again control back signal will be given to the ZigBee here with the help of the Node MCU, and this will be transferred to the router, and it will be given to the Arduino. From here, the relay will be controlled with the Arduino here. This is a circuit. So these prototypes are published in the IJSTR, which is a Scopus-based journal. And these are the conclusions from my research. In the very initial work, in the literature, smart grid simulators and their suitability for the home energy management system is discussed, and the existing hardware implementations and functionalities and DR programs for HEMS is also discussed, and the motivation, setbacks, and the solutions for co-simulations are also discussed here, and the compatibility of the power system simulators and communication system simulators for smart grid and home energy management systems are also discussed. In the second work, that is a demand response program, price elasticity based DR program with the influence of loss aversion is also implemented, and it's tested for the DR programs with the different seasons, and all the financial and the technical viable and unviable conditions are also discussed here, and the outcomes of peak load scenario and the equal loss scenario are also discussed, and the effects on the technical parameters like peak load reduction and total demand serving capability with the application of different loss aversion and rebate values and cross elasticity values are also discussed here. And in the third work, a water filling energy distributive algorithm in coordination with PEV as a secondary storage is used, is implemented, and it minimizes the total cost of energy without losing the comfort, and it's as well as it improved the comfort level also, and it has shown the good effect in the grid flattening, which reduces the stress on the grid, and stress on the battery also is reduced with the life cycle improvement by reducing the number of charging and discharging cycles. A small prototype is also prepared to make sure the energy efficiency programs for the HEMS. And the future works, actually I have in my demand response work, I've taken for a single day of each season. So a 1 year data we can take and we can analyze them. For which month, which DR program is suitable, which is the better one. Based on the seasons also we can make the conclusions, and all our conclusions can be trained in a real time, and with the help of the machine learning and reinforcement learning models, we will get the more accurate results in implementation here. Real-time system we can implement with the help of the machine learning by training the data here. So, and from the knowledge of my works, I can be able to go ahead with the smart grid labs works and energy management test beds in further of my works. So this will be the nature of the works we can do in future with the help of the smart plugs and thermostats and lights. The total energy information will be obtained. Raw data will be obtained from the internet also, like the status and the dates. Those data will be obtained, and the pre-processing will be done based on our requirement and based on our conclusions. We can pre-process the data and we can real-time model the system, and these will be and the analysis can be done as a predictive energy management and the real-time energy management. And these can be done with the help of the machine learning regression problems and classification problems and different types of supervised and unsupervised learning methods. And these are my list of publications. Conferences presented. 2 conferences are presented in ICASIC 2020. And these are the journals published. First one is IET GTD, Generation Transfer SCI Expanded. And in the second one, Elsewhere Sustainable Energy Grids and Networks, which is an SCI Expanded with an impact factor of 2.5. And this is a Scopus-based journal. This prototype was published in the Scopus-based. And the demand response work, that is also under communication with the Elsewhere Sustainable Energy Grids and Networks, which is an SCI Expanded with an impact factor of 2.532. And these are the references I have gone through. Thank you very much.
It's a very good presentation. I think you have consolidated everything, whatever work you have done. So now I request the research scholars and the faculty members who are having a query in this work, please start. Professors, I think expert members are there. I think they can start.
Rajendhar.
Yes, sir.
Yeah, it's a very good presentation. Also, the work is very good. Even it is matches with your objective, what you mentioned in the initial slides.
Yes, sir. Thank you.
See, I have some suggestion. See, in the literature survey, you described about the work, but you didn't mention from where you have cited. It's better you try to cite the journal in the slides.
Okay, sir.
You go to the slides, Rajendra. You can go
Yes,
to
sir.
the slides.
Can you go to some some literature survey, no? Maybe slide within 5 to 10. Yeah.
Here itself I have included, sir. Complete
Oh,
references what I have taken.
okay, okay.
These are only the references, main references I have taken, sir.
Okay, just go back. Just go back. Go back.
Here, sir.
Yeah, go back. Yeah, here and all I'm saying. So here at the
Here.
bottom, yeah, you can write it from where you are.
Okay, sir.
So these papers only listed in the literature survey. You have shown on slide no now.
Yes, sir.
These are the works which is described in there.
No, sir. This is related with the literature, sir. Actually,
Yeah,
for
literature only. From where you have taken? From which paper? Either it is journal or conference paper.
journal papers, sir.
Yeah,
Actually,
that's what we are asking. You can mention at the bottom.
okay, sir.
Okay.
Yes, sir. So these are the
Even in
journals. I
the
could
another one column you can add, and you can
And
put the year and journal name.
yeah,
okay, sir. In the down, I will put, sir.
The
That.
yeah.
author, I think he has put the author. There itself, I think you can put the journal name also.
Okay, sir. I will try to incorporate, sir.
Okay. And regarding the equation, PV mobility model equation you have shown, no?
Yes, sir.
Did you derive or it is adapted from any references?
Sir, it's have been taken from references only, sir.
Okay, okay. See, again, I have some little doubt regarding lambda.
Okay, sir.
On what basis you are fixing the lambda for PTR2 and PTR3? I think you are maintaining the same lambda for PTR2 and PTR3, right?
Yes, sir. PTR 2 and 3 lambda is same, sir.
Same. Okay. So why you are taking lambda is equal to 0.5? Is there any practical reason? Is there or?
No, sir.
Mm-mm.
We can vary the value also. Why? Because just to actually my intention is to represent the losses. Actually, in many of the literatures and previous papers, it's taking as a linear. Losses will be equal are proportional to the gains. So here, to to make the system more practical, that lambda value has been considered. That steeping curve has been implemented in the system, sir.
Okay. See, can you go to slide 25? Yeah. Here, these are all simulated results, right?
Yes, sir.
The same thing. Did you verify it in the practical also?
Practical, only MATLAB simulation I did, sir. I
Only
didn't.
MATLAB simulation. Okay.
Yes, sir.
No,
I
in the
haven't.
latter part, yeah, okay. So in the latter part, I have seen some practical circuit with Arduino.
Yes, sir. That are basic circuits, sir.
Basic, okay, okay.
Yes, sir.
So
These, sir,
yeah, yeah. Mm-hmm.
these implementation in real time, like Typhoon also, I will try to incorporate. So further, these exact DR programs with
Yeah, this is yeah that is my next suggestion I'm going to give. That's what.
yes.
See, you can replace Arduino and all. See, when you talk about the real-time scenario, the Arduino will not support lot. So
Okay.
since we have many real-time software like OpenRT or DSpace and Typhoon, you can try with your model with the real-time software.
Sure, sir. I will try.
Yeah.
Actually, that work has been done in the initial days, sir. Very initial days of my work, I did that work, sir.
Okay. Okay.
And real time and hardware parts for my exact objective, I have not tried now, sir. I have to start now.
Okay. Okay. Okay, Rajendhar. All
Okay,
the
sir.
best. Yeah. Thank you.
Thank you, sir. Thank you very much, sir.
Rajendhar, can you note down all the points, okay, one by one?
Yes, sir. Yes, sir. I'm noting down, sir.
Yeah, Rajendran.
Yes.
So, yeah, as publishing point of view, good that you have good publications. But when you're writing it in the chapters, you have to write properly so that that link between the chapters. Can you explain me the commonality between the three work? Because last hardware, yeah, as you rightly said, it is IoT implementation for a small appliances for controlling.
Yes, sir.
And second, last is this water filling algorithm.
Yes, sir.
That is for energy conservation. You are minimizing that. And
Yes, sir.
the previous one is the different pricing scheme.
Demand
So,
response.
of demand response. So, so how you are going to manage the commonality on all the three things? Because is that environment what you have taken is same? Because that doesn't looks like same. So
Yes, sir.
what reason for going for that algorithm? Because you are doing only with one algorithm and you are not compared with any other algorithm also.
Okay, okay, sir.
So then previous chapter, for example, anyhow you are going to put you will be putting this as different chapters, correct?
Yes, sir.
So when you are putting different schemes, so how you are going to link this? For example, after this chapter, why you are going for this algorithm? You need to justify, correct? Then after
Yes, sir.
that, this algorithm, then what is the reason for going for this hardware? There should be a link. There should be a
Okay.
reason for moving to the next work. So how you are going to justify that? Because there you need to really work hard, I think, to link these three work.
Okay, sir. I will do.
So yeah, that you have to carefully write because peps individual paper wise it's fine, perfect, good.
Okay, sir.
Okay, but when you're writing it, you need to properly justify the reason for going for the second work because or else it looks like as though three are different work.
Yes.
Okay, there are
So,
chances. Okay,
okay.
where a reviewer may feel that there is a totally a mislink between these three work. Okay, so
Oh,
you need write at the beginning, at the end properly, such that why you went for this algorithm because the objective of that algorithm looks different from the previous work. Okay, there the objective is, or are you justifying that this is the reason for going for this specific algorithm, or somewhere that gap should not be seen or visible. Okay.
okay, sir. I
Yeah,
will
that is
check it.
yeah, that's very important thing. And for each cases, for each work, you can mention the list of assumptions because there will be a lot of assumptions involved during the
Yes.
process. Okay, so you can clearly write so that unnecessary questions you can avoid from the reviewers.
Okay, sir.
Okay, because you can tell what is your scope, what is this work, what are all the environment in which you are handling, all those things alone.
Okay, sir.
Okay, and how you are validating the results what you get from this water filling energy algorithm?
I compared just actually one base setup was initially I have
Okay,
motivated from one of the thesis, sir, from one of the Ghent University thesis that is from Belgium.
Acha, the
They
same environment they have taken.
same environment they have taken, sir. They have used some PSO algorithm.
Acha,
But
acha. Then fine.
my intention is to take the energy distributive algorithm. Actually,
Okay,
the
okay.
base work they have did. The base work I have did with the GA, and then these are the further implementations, sir. Water filling algorithm.
In a base work means what you are telling.
That in case one, the complete appliances have been taken, and the optimization has been done with the genetic algorithm, sir.
Acha, acha. Okay, okay. Right, right. So that validation part, that point, and reason for going for a Simulink, is that only for time domain reason you went for Simulink or any other specific reason you choose the Simulink model?
Actually, in one of the reference means that Pecan Street project, this demand response paper completely motivated from the Pecan Street project, sir. The
Okay,
base was when I'm searching about the literature, uh, just whatever the model initial base model prepared for the work is
okay.
also
They also
is
used MATLAB Simulink.
Yes, sir. They also used it in the MATLAB. So for that, I replicated the same work, and then further implications of the complete seasonal analysis and different demand response programs that I have incorporated, sir, and then compared.
Okay. Okay, pa. Right.
Thank you, Dr. Prabhakar. And Satish sir. Sir,
No,
Ravi
sir.
sir for
Sir,
class.
no problem. We can proceed, sir.
Okay.
Thank you, sir. Thank you, sir.
Okay, sir. So Ravi sir left for class at 3 o'clock. So are there any questions from research scholars side?
Nowadays, research scholars are not involving in any discussions.
Sir. At
Seeing
least they
in
joined, that is good news. They joined on time so that we are able to start exactly at 2:30.
Sir, one question from my side, sir.
please.
Okay. Sir, you have did the energy management, sir? Yes, sir?
Yes, sir. Yes, ma'am.
Okay. From where to where you have managed that power, sir? Or else vehicle to grid or grid source to source? Which source to source you have managed, sir?
This main grid, actually, the source side is grid is the main source, and the
Okay.
appliances PV we are having, and CHP we are having, and battery also we are having, ma'am.
Okay.
So from this battery to the PEV for the grid flattening, the main power balance is between the PV, CHP, and the battery as a source. And in addition to this, now PV has been considered as an additional storage. So whenever it is required from these all sources to PEV or PEV to grid, madam. Both conditions.
Okay, grid to PV and as well as the PV to grid.
Yes, ma'am.
Based on requirement, you are managing the power.
Yes, we are finding the charging condition and discharging condition, ma'am. That energy available to charge, energy available to discharge. Based on that, we will decide, ma'am.
Okay, okay. Okay, sir. Thank you.
Thank you.
Any other query? Okay, so I think Mr. Rajendhar, you have noted all the points, whatever the
Yes, sir. Yes, sir. I'm not.
feedback.
not.
Okay, incorporate everything before the synopsis.
Okay.
Again, I feel that some more the experimental part, what I have seen, I think you can, in the first two objective, any experimental work you have carried out by using our hardware facilities?
No, sir. I haven't started anything, sir, on that.
So, because we are having a lot of facility, whether you can use anything for your research, in at least in the future work, you can say all the experimental work, what you
Yes.
can how we can extend your work through experimental facility which are available in VIT.
Sure, sir. I will try to use it, sir.
Because your juniors, at least you can say this information to your juniors, so they can at least they can do some experimental work.
Sure, sir. Okay, sir.
Okay, Belvin.
Yeah, yes, sir.
So I thank everyone for joining us in the Colloquium presentation.
Okay.
So thank you, Belvin, and so Rajendhar, you incorporate everything. So,
okay, sir. Thank you, sir.
Okay, thank you all research scholars and panel members for your for sparing your valuable time and for your valuable suggestions given. Thank you, Professor Prabhakar Karthikeyan. Thank you, Dr. Satish Kumar, Professor Ravi, and Professor Thermalevasan.
Yes.
So we will send you the mail to get your e-approval for proceeding further. Thank you all. Thank you once again.
Thank you, professors, specifically panel members. I have to thank them. Thank you for your wonderful feedback. Thank you. Thank you.
Thank you, sir.